maybe not.
No, actually, I guess we didn't finish chapter 3. We didn't cover STP. What about stuff from earlier? Yeah, I didn't quite make it through all of chapter 4, so let me just finish off STP. Okay, standard temperature is 0 degrees C or 273 Kelvin. And standard pressure is 1 bar, 1 atmosphere. STP is not that useful. It's not that useful because how often do you work inside a 0 degrees C laboratory? Never. And so that's what makes it not very useful. They just use it as some arbitrary reference point, but if they're going to pick some arbitrary reference point, then they should use room temperature. Do you recall room temperature? 25 C. And that's much more useful. And so in all the time I've memorized STP, I've only used it like once, I think, if even. I was just looking in some chemical manufacturer's catalog and I saw STP. But there are some calculations here that we can do. The volume of a sample of nitrogen gas is measured at 3.62 liters when it is at 0.843 bar and 16 degrees C. What is the STP volume of the nitrogen gas sample? So if we're looking at this, we have pressure, volume, and temperature. So if we look at the original nitrogen gas sample, it had a pressure of 0.843 bar, a volume of 3.62 liters, and a temperature of 16 degrees C. We can't leave this one, but we can leave these two. It's not a problem. So 16 degrees C would be 289 Kelvin. And then we want to know what is its STP volume. So V2 is unknown. Well, what is standard pressure? Yeah, it's going to be 1 bar. And then standard temperature is going to be 0 degrees C or 273 Kelvin. So we'll take our combined gas law, P1 V1 over T1 is equal to P2 V2 over T2, and solve for V2. V2 is equal to P1 over P2. And then we're going to get T2 over T1. This is a pressure fraction, temperature fraction, times the original volume, P1. So what happens to the pressure fraction? So we go from P1 to P2, the pressure went up. P1 is 0.843 over 1. The units cancel in this case. The bars cancel the bars. So as long as the units are the same, you know, it could be atmospheres, it could be millimeters mercury, torr, whatever. As long as they cancel, you're okay. the pressure fraction goes up, but the fraction, I mean the pressure goes up, but the pressure fraction goes down. Now it's less than 1. Let's look at what happens with the temperature. The temperature goes up, and the temperature fraction, 273. Oh, actually, the temperature doesn't go up. The temperature went down. Sorry. The temperature went down, so the temperature fraction is actually going to be less than 1. B1 is 3.6. And so both of those are going to make the volume smaller. So we're going to get 0.843 times 273. Even though the units here, Kelvin cancels out Kelvin, it has to be in Kelvin. This won't work in degrees C. So for example, if you had 0 degrees C in the denominator, then this fraction would be infinite. Which isn't right. So 273 divided by 289 times 3.62 is 2.882. And so if you increase the pressure and decrease the temperature, the volume should contract. And that's what we see here. 2.882, which rounds to 2.88 liters. There's one additional law, and that's the relationship between pressure and temperature. We did pressure and volume, temperature and volume. So we link those and get pressure and temperature. This is called Gay-Lussac's law, or Amaton's law. Pressure proportional to temperature. But, you know, Amaton's law, or Gay-Lussac's law, Charles' law, Boyle's law, all those laws you don't need to remember. All you need to remember is the combined gas law. And so I'm not going to ask you a question like this. I'm not going to ask you, is Charles' law pressure and volume or temperature and volume? I wouldn't necessarily ask you that on a test, but we just had that lab. And that lab said that Charles' law is the relationship between pressure and volume, or temperature? Yeah, temperature and volume. You might have known that. This is the last slide, and there are no examples here of that. So that's the end of chapter 4. Were there any questions on chapter 4? So far? How about chapter 3? Or
So we have like calculating something that's a quotient, and the numerator is like a sum or difference, and then the denominator is like a product. Like, do we do the sig fig separately then at the end?
Yeah. You would have to do the sig fig separately.
It's like for the top and then the bottom, and then at the end you do it.
Yeah. Yeah. First you'd have to do the addition or subtraction or whatever it is, and then the division, the multiplication. So let's say I had 2.0 times 1.0 minus 0.91. How many sig figs am I allowed in my final answer? Two sig figs in my final answer? Anybody else have a different number, or everybody gets 2 sig figs? This is a bit of a trick question because it looks, this is 2 sig figs, this is 2 sig figs, this is 2 sig, everything has 2 sig figs, so we expect 2 sig figs at the end. But what we have to do is we have to do the subtraction first, and subtraction, we don't care about sig figs, we care about decimal places. And so here the uncertain digit is in the first decimal place here. But in the second number, the uncertain digit is in the second decimal place. And so what happens is if we do the subtraction, that puts the uncertain digit here. So what we're going to end up with is 0.0, well, actually not 0.0, 0.1. Oh, no, 0.09. Is that right? No. Oh, actually, this wasn't a great example. But if we do this, you know, we're only allowed one uncertain digit. So here it is. Can we go ahead and tack another 0 on there so we can call this 0.090? No, because that would, all the digits past here are uncertain. And since we're only allowed one uncertain digit, then how many sig figs are we going to end up with? Just one. And so the final answer is only going to have one sig fig. I could have picked something else, make it a little bit easier. And that's a kind of a trick question because you have to do things separately. So, you know, we could have 3 sig figs here, and 2 sig figs here, and 4 sig figs here. And so how many sig figs am I allowed in my final answer? 2, 3, 4. How many sig figs in my final answer? One sig fig. Not 2, not 3, not 4. Why not? None of those.
Take the difference of 1.00 and 0.95, the uncertain digit is going to be that much space.
Yep. Yeah. So we do the subtraction first. 1.00, uncertain digits here, minus 0.95, uncertain digits here. And so this is going to give us 0.05. This is one uncertain digit. So just one sig fig. Do that. And then times this. So 1 sig fig times 4 sig figs. This is 1 sig fig. Okay, does that answer it very much? Are there any other questions? Chapters 1, 2, 3, 4.
On the sample exam, there's something about the chemical theory. What is that?
Chemical theory. Has everybody looked at the sample exam already? Maybe I should wait to talk about that. You could ask me during the office. Alright, that's okay. But you should treat this like a regular test, you know. What number was that? Just here.
23.
Charles' law was derived from chemical theory. Charles' law was, what is chemical theory? Theory of chemistry. What is the theory of chemistry? When you use the theory of chemistry, you can make predictions. So, for example, if you use the theory of chemistry, you could predict the color. Do you know what color chlorine gas is? It's yellow-green, green-yellow. That's what chlorine gas is. If you've never seen it, then you probably don't know what color it is. But if you've seen it, you probably memorized the color of chlorine gas. If you can recall it, you've memorized it. And so I talked about chemical theory in relation to memorization. You know, what would be easier? To memorize that chlorine is yellow gas, yellow-green gas, or to derive it from chemical theory? Yeah, to memorize it. And so some people might go, you know, what's the point of memorizing? Is memorizing not learning? I hear that all the time. Memorizing is not learning, but I disagree with that. You need to do some memorization to learn. Otherwise, it's too much. It's too much. Even the top-end theoreticians, you know, they had this thing in physics with the Large Hadron Collider, you know, the most powerful atom smasher ever made in Switzerland. And so they're very excited. There are a whole bunch of YouTube videos and other things, documentaries made. And it was about this, finally they have something that could test the theoreticians' predictions. And so they had all these theoretical physicists that made predictions about what's going to happen. Did you hear about it? And so finally they're going to test it using an experiment, factual observations. And so not to downplay anything, but did the theoretical predictions pan out? Does anybody know? Theoretical predictions were like this. They're expecting, I think, a line at some energy, but they didn't see it. It didn't come at that particular energy. It was at a different energy. And so that meant they had to go back and rethink it a little bit more, basically. And it doesn't surprise me, because that happens in chemistry too. You have people, the theoreticians, who are going to predict, okay, this should be the best drug to use. And they can design it and then have some kind of target and then try to make it and then see how effective it is. But that's not going to put the experimental chemist out of a job, because why? Because theoretical calculations are so difficult. They're not easy to do, these theoretical calculations. And so you need both theoreticians and experimental chemists, because everybody, the theoreticians and the experimental people, want to understand properties of matter. And so if you want to know the properties of any piece of matter, what do you do? Well, you have to observe it and measure it. And so what you do, I want to know the properties of chlorine, so you have to observe it. You have to observe that, hey, this is a green gas, it's a gas, etc., etc. That's observation here. Observation is that. So let's say, okay, we did it. Now we want to go to fluorine gas. Okay, what do you do? Well, what color is fluorine gas? Chlorine gas is green yellow. So what color is fluorine gas? What color is bromine gas? Is bromine even a gas? What color is iodine gas? So some people say, it's not necessary to memorize, because you don't need to memorize that kind of stuff. You could just figure it out theoretically. But is it so easy to figure this stuff out theoretically? No, because the math is so difficult. And so the other option is, well, then does that mean you have to take observations of every single thing you want to know? Every single thing you're going to have to measure. Measure its color, measure its properties, measure this. No, that's too much. And so what we want to do is we don't have to want to memorize everything, because that's overwhelming. And so rather than memorizing every single little detail about every single little piece of matter, what we do is we look for patterns. If we can find patterns, maybe, maybe there's a pattern or trend to this where, if you kind of know the pattern, maybe you can predict it without actually having to measure it. And so we look for patterns. Sometimes those patterns are very, very good patterns, which might end up being wrong, or we use theory. And so our approach to understanding the properties of matter comes from knowing some observations, knowing some patterns, and knowing some theory. Is if we know some observations, just have some factual stuff memorized, having those memorized will help us develop, or at least see the patterns that are underlying these things, and then use theory whenever we can. Because we want to understand the properties, both the physical properties and the chemical properties of matter. Now, to have to observe it is one thing. So, for example, there are people who do this for every single piece of matter. They'll test it, observe it. These are people who go out, in the rainforest, and they look for new medicinal drugs. You know, there might be some kind of herb or some kind of tree that the indigenous people are using to cure some disease, or so there might be some molecules that are yet undiscovered in the rainforest that might prove to be a potent drug. But that's like, how many molecules are in the rainforest? If you think, how many plants are in the rainforest? Lots, and so there's probably a lot of biomolecules out there. That's a tremendous thing. So maybe we could narrow things down. Maybe there's a pattern. Maybe you just look at specific things. But what drug companies do is, do you think drug companies are going to send out huge teams of researchers out into the rainforest to look for these? No. What drug companies are going to do is they're going to want to do this theoretically. That is, they'd like to be able to model this and then figure out what the target drug is. But it turns out that even with that modeling, the calculations are very difficult. And so I end up giving some examples, like did I talk about the blue LED in the class? The blue LED was a race between the theoreticians and the experimental chemists and material scientists. And the theoreticians were predicting this composition. Actually, they were predicting because the properties of matter are based on the composition and and the structure. And so the theoretical chemists were looking, okay, with this composition and this structure, that's a good candidate for the blue LED. So then some experimental chemists would come and try to synthesize that. And then you had the person who discovered it is more brute force. They just mix up different compositions and see what works. Mix it up, see what works. Mix it up, see what works. Obviously, they don't want to do it blindly, and so they use some patterns and as much theory as possible to find it. But this is more brute force, just trying different things to see which one works effectively. But for us, we're going to try to incorporate all three. So, ideally, we would like to use the theory of chemistry to be able to predict everything. The color of chlorine. Why is water a liquid at room temperature? If you didn't learn that water is a liquid at room temperature, could you prove that to me theoretically? Give me some kind of mathematical or theoretical reason why water should be a liquid and wax is solid. And so in life, we do the exact same thing. In life, we use all of this. The theory of chemistry, I don't know if you caught it, but the theory of chemistry is called quantum mechanics. I didn't really talk about it at all because we're going to be talking about it pretty soon, quantum mechanics. And it deals with electrical interactions. But in that particular, to answer that particular question, you don't need to know what the theory is. You just need to know how science works to answer that particular question. In fact, well, that one's pretty, everybody should know this because we had the lab. So we'll just cover this one. Charles' law was derived from chemical theory, true or false? False? Okay, what was it derived from? Yeah, it was derived from Observations. Here are the observations. As the temperature increases, so does the volume. Keep increasing the temperature, the volume increases, the volume increases. Is there a pattern? This is not in order. Is there a pattern? Yes. So here's the pattern. We call it a graph in this case, but the pattern doesn't have to be a graph. It could just be some kind of mathematical pattern. Well, the graph is a mathematical pattern in this sense. But it could be some other pattern, which yields an empirical equation which we call as well. So these are the observations. You could derive Charles' law from theory as well, but that's not how it was originally done. If we derive Charles' law from theory, have some equations that come from kinetic molecular theory. Kinetic molecular theory is kind of the quantum mechanics of the gases, molecular gases. From these equations from kinetic molecular theory, we can derive Charles' law.
Project management on Monday.com. This is what it looks like, and this is what it is.
So we'll do this as a abridged version of this.
इसमें स्टूडेंट हमने जो देखा था आपका लास्ट में वो आपने समझा था प्रेशर एनर्जी आपने देखी है उसके बाद आपने रिलेशन बिटवीन कैल्विन टेम्परेचर एंड काइनेटिक एनर्जी
I guess this isn't in English.
की मदद से स्टूडेंट आज हम
But anyway, math, you don't need English in math. Let's see the math. Okay, let's skip ahead here. So we get these equations. These equations come from the theory, kinetic molecular theory. Then use this. This is like Newton's. Some of this is like Newton's laws here. This is actually. Do you remember doing this? Deriving Charles' law from theory? Yeah? No, obviously not. Where did Charles? How did we do Charles' law? Yeah, through observation. It's just simple mathematical pattern. That's what we did. We could have done it theoretically. Obviously, the theory has to be a fundamental explanation of Charles' law. So when we look at the mathematics of the theory, we should be able to derive Charles' law. We should be able to derive Boyle's law. We should be able to derive Hamilton's law. All those from theory, the basic theory of chemistry, which we can. You know, because otherwise the theory is no good. And so, yeah, once we get the theory, then we can work backwards and derive everything, not from an observational or a factual, you know, experimental facts, but from a purely mathematical, theoretical point. This is Dalton's law. This is another law we're going to talk about later on when we come back to gases. And so that question is just the scientific method. This is kind of interesting. Here's another one, kinetic molecular theory. Gases. Okay. So there are some people who say, oh, you don't need to memorize anything. You can just determine everything theoretically. Do you want to do that? Look how much work this is just to derive Charles' law. You don't want to do that for everything. Okay, other questions? Okay, on the other hand, you don't want to have to memorize everything, because if you have to memorize everything, then it's way too much. So example, why is a hydrogen atom different than an oxygen atom? Do you want to have to memorize every single thing? An oxygen atom weighs this much, a hydrogen atom weighs that much. An oxygen atom is this big, a hydrogen atom is that big. You know, in terms of behavior and that kind of thing. No, it's a bit much. And so the key thing is this. Sometimes the theory is a bit much, so we look for patterns. Hopefully that'll help us. Sometimes the theory is not too bad, so we try to apply as much theory as possible. Other times, you know, both of these are pretty difficult, so we just work on strictly memorizing little facts about the difference. So let's go into chapter 5. You know, in chapter 5, we're going to talk about Dalton's atomic theory. And then the law of multiple proportions. Did the law of multiple proportions come from theory or observations? Yeah. This one actually came from theory. This is the only law that came from theory that you know. All the other laws came from observation. Remember, this is the law that the theory actually predicted. The law that led to atomic theory is called the law of constant composition, which is not shown here. The law of constant composition. That is, water's always H2O. You know, have you ever seen any H1.9O? It's constant composition. That's what led to atoms. Okay, then we're going to start looking at the parts of the atom. What atoms are composed of. Electron is one of them. And then how they're structured. One of the key experiments here is Rutherford scattering experiment. So electron is called a subatomic particle. We're going to look at the subatomic particles and how they're structured. Rutherford scattering. There are 3 types of subatomic particles: proton, neutron, and electrons. We'll talk about those. We'll talk about isotopes, and the nuclear symbols, atomic number or mass number. Not all features of Dalton's atomic theory are considered valid today. Some parts of Dalton's atomic theory have been abandoned. And we're going to talk about the mass unit, the atomic mass unit. The atomic mass unit is just a different unit. I mean, we have different mass units. The gram, the pound. You know, how is a pound defined? Well, maybe you don't know. I don't, actually. I don't know. But it's okay. I don't need to know that. How's a kilogram defined? I probably should know that. How's a kilogram defined? Well, a kilogram is 1,000 grams, but how's it, when I say how's it defined, you know, is this 1 kilogram? Or close enough? What is 1 kilogram exactly? Yeah, it's that metal. That metal, and how many bell jars was that? Was it 3 bell jars? Yeah. They want to protect it. But you know, the metal doesn't need that much protecting, because what kind of metal was that? It was platinum. Platinum's known for its resistance to corrosion, for maintaining its luster. You know, something that's pretty unreactive like that's called a noble metal, like gold. You know, platinum and gold are both considered noble metals. So that's reason 1 they're using platinum. Do you know reason 2 they're using platinum? Reason 2 is probably because they don't want to buy huge bell jars, because platinum is a very dense metal, and so it doesn't take much metal to make 1 kilogram. If they use aluminum, the bell jars would be huge. You know, they have bell jars like this, and not only that, aluminum is pretty susceptible to corrosion. So aluminum's density is pretty low compared to platinum, and therefore you'd need a big chunk of aluminum compared to a small chunk of platinum. But not only does the metal have platinum, it also has another very rare element. Iridium, yeah. Iridium is very dense. All the iridium on Earth is, or most of it's, I think, thought to come from a asteroid that hit. Okay, so that's how the kilogram is defined. And then we have something like this. The kilogram is just a chunk of metal. That chunk of metal is exactly 1 kilogram. And somebody's keeping safe watch over it. And so now, if you're ever worried if you have exactly 1 kilogram, you know what exactly 1 kilogram is. There's something called the atomic mass unit. The atomic mass unit is convenient for weighing things like the hydrogen atom. The hydrogen atom weighs about 1 atomic mass unit. Weighs about 1 atomic mass unit. And so, you know, how's the atomic mass unit defined? Do they have a do they have something locked up in a vault in France? This weighs exactly 1 atomic mass unit. What weighs exactly 1 atomic mass unit? Because a hydrogen atom doesn't quite weigh, you know, it weighs a little bit more than 1 atomic mass unit. And so they'd have to lock up something in a vault in France, but it can't be a hydrogen atom. It has to be something else. What weighs exactly 1 atomic mass unit? That's a hard question to answer. Well, maybe it's an easy question to answer. What weighs exactly 1 atomic mass unit? What weighs exactly 1 atomic mass unit? Nobody knows. You know why? Because there's nothing that weighs exactly 1 atomic mass unit. If there's nothing that weighs exactly 1 atomic mass unit, what are they going to lock? In a bell jar in a vault somewhere in France. They don't have some little tiny particle that they call 1 atomic mass unit and weigh it. And so we have to look at how the atomic mass unit is defined. So when they say defined, they don't want the number, they want to know how it's defined, or I want to know how it's defined. And so we'll be talking about that. This one's an important one to know how it's defined. And that's why it's important, unlike the pound down here. Okay, then we're going to talk about natural isotopes, naturally occurring isotopes, and look at the periodic table, you know, the arrangement of the elements in the periodic table. We have different parts of the periodic table called the main group, metals, nonmetals, transition metals. So we'll start off with the Dalton's atomic theory here. Okay, the parts of the Dalton's atomic theory you don't have to bother memorizing. Plus, it's already changed. So as long as you know that matter consists of atoms, you're pretty much that's it. That's all you really need to know. And then you need to know a little bit about the atoms. So each element is made up of individual particles called atoms. We already know that. Atoms are indivisible. Can you break atoms up into like mini atoms, mini compounds? No. So if you have a single atom, you can't break it up. Well, can you break up an atom? Is it possible that, yeah, you can break atoms apart, but they're going to break apart and form subatomic particles, which don't behave like elements. Okay, all atoms of one element are identical in every respect. This turns out to be wrong. Atoms of one element have the same, chemical properties, but they might weigh different amounts. And so I think I mentioned the water. Did I mention about heavier water molecules and lighter water molecules? Talk about that? So actually some of the oxygen atoms in this water weigh more than others. Some weigh less than others. Could you taste the difference between the heavier water and the lighter water? No, you can't. But if you were to separate it, so if you removed all the heavier water molecules from here, then definitely they would weigh different amounts. And the heavier water molecules would weigh more than the lighter ones. And therefore they would have different densities. So they would be more dense. Okay, atoms of one element are different from atoms of any other element. That's true. Hydrogen atoms are different than oxygen atoms. But, why? This is just statement of fact. Yes, it's a factual observation. We can memorize that, but wouldn't it be better if we knew something more about, theory, patterns, other stuff? But this really doesn't explain much here, or describe much. Atoms of one element combine with atoms of other elements to form chemical compounds. So compounds are two or more elements combined. Like water, H and O. And so these we don't need to worry about, nor do we really worry about these. Victoria. An element is made up of atoms. All atoms of a given element are identical. Well, some weigh a little bit more, some weigh a little bit less. We'll talk more about that later. But otherwise, they're pretty close to being identical. If you look at that, let's just look at, is that solid, liquid, or gas?
Solid.
Is that amorphous or crystalline? Atoms cannot be created or destroyed in chemical reactions, but now we know in nuclear reactions, atoms might be created and destroyed from other atoms. So, all atoms of any given element have the same properties, including mass. No. We should rewrite this. All atoms of any given element have the same chemical properties, but might have different masses. And so a heavy oxygen and a light oxygen are going to weigh different amounts, but they'll have the same properties, chemical properties. Physical properties will be different. For sure, like a hydrogen versus an oxygen are going to be different. Atoms of different elements may combine in a ratio of small whole numbers to form compounds. So this is 2-to-1 blue, red. This is 1-to-1 blue to red. All right, that was the atomic theory. And then one of the predictions that came out of Dalton's atomic theory is the law of multiple proportions. Here, atoms are going to consist, if there are two or more molecules or two or more compounds that consist of the same two elements here, they're going to occur in small whole number ratios. This is a repeat of what I said before, but it's 1-to-1 here. It would be a 1-to-2 here, 1 carbon, 2 oxygen. So simple whole number ratios. So this is the kind of stuff we were already talking about, but to better understand this, to dig deeper into the theory, we need to know how things are structured and what they're composed of. And so let's look at this. You know, if I had an oxygen atom versus a hydrogen atom. When we look at an oxygen atom and a hydrogen atom, Dalton's atomic theory says that atoms of different elements are different, therefore they're going to have different properties. Well, that's not enough, because that just means memorizing things. So for example, if you want to know the differences in properties between hydrogen and oxygen, you've got to memorize all of them. Memorize all the properties of hydrogen, memorize all the properties of oxygen, then you can tell me the difference, right? But that's overwhelming, because then we have to do that for everything. So what would be much better than having to memorize this is to see if we can see some patterns, or to see if we can apply the theory underlying this. And so we're going to dig deeper into the theory. Now, digging deeper into the theory, one of the first things we want to know is, you know, composition and structure. How did these two differ compositionally and structurally to cause a difference in properties? As far as composition goes, then all atoms are made up of the same 3 subatomic particles. And so there are going to be 3 subatomic particles. Okay, the first subatomic particle is the electron. Just talked about it there. And then that has the symbol E minus, or E. Then the second subatomic particle is called the proton. P plus, or just P. The third subatomic particle is called the neutron. It's given N, or N0. So those are our 3 subatomic particles. So the first thing is we look, what is the compositional difference between oxygen and hydrogen? You know? And then what's the compositional difference between heavier oxygen and lighter oxygen? And then what we look at is the structure. When we look at the structure of the atom, we have something called the nuclear atom model. This is structure part 1, nuclear atom model. And so maybe based on this, you know, we could figure out, you know, the patterns. The patterns that we're looking for is there a correlation between certain compositional features and the properties? Is there a correlation between, let's say, number of protons and properties, number of neutrons, number of electrons? Is there a correlation between the structure and the properties? Those are the patterns we look for. So for example, you know, diamond is made up of what? Yeah, is it pure, or? It's pure carbon. Diamond's made up of pure carbon. Graphite is made up of pure carbon. Both of those are pure carbon. So what's the difference? Well, they're totally different. And they're totally different because of the structure. Structurally, the carbon atoms are arranged differently. They are arranged differently in terms of what we call crystal structure, the arrangement of the crystal. And not all crystal structures look like this. This is too simple. In fact, when we look at a real crystal structure, most of them aren't packed like this, you know, in neat rows. What we see is that this row is offset a little bit. This row, you know, to better pack things together, this atom fits nicely in this little well here. So all these are offset a little bit, packed. And so, yeah, so structurally they're different. So what we're going to do is we're going to start looking for as many patterns as we can, so we don't have to memorize so much stuff. But first we got to memorize. First we got to memorize the basic particles. Then we got to memorize the basic structures, and then we'll see, you know, other patterns that we can use to lessen that. So a certain amount of minimum quantity of information needs to be memorized. And so, okay, so the first thing we're going to look at is electron. So what can you tell me about the electron? Well, electron is a piece of an atom, or part of an atom. An electron is a subatomic particle carrying a unit negative charge. What they mean by unit negative charge is this: unit's 1. And so it's carrying a -1 charge. That's what that sentence means. And so the charge of this is -1 or 1-. It doesn't really matter where you put the minus sign. Here I would put it in front, but the author put it behind, which is fine. Okay, the electron is quite small. When we look at the other parts of the atom, what were the other parts of the atom? The other parts of the atom are the protons and neutrons. It turns out the electrons are really small compared to the protons and neutrons in terms of weight. In terms of weight, an electron is about 2,000 times lighter than the hydrogen nucleus. Well, what is the hydrogen nucleus? Hydrogen, it turns out, has a nucleus that consists of only one particle, and that's the proton. And so this should be written. It has a mass of 2,000 times less than the proton. So, in other words, a proton weighs about 2,000 times more than an electron. So the proton is much more massive of a particle than an electron. The symbol is E- here. Its discovery is credited to J.J. Thomson. Let me talk briefly about the discovery of the electron. You know how the electrons were discovered? The discovery of electrons occurred in the cathode ray tube. Cathode rays, have you heard of cathode rays before? Cathode rays are essentially a controlled lightning bolt. And you know what a lightning bolt consists of, like Thomas Edison was flying the kite, but do you know about that pretty much? Lightning bolts consist of electricity. Electricity consists of electrons. That's what's conducting it. And so here, what we have in these, this is a cathode ray tube, the fluorescent lamp. And in that tube, we have a controlled lightning bolt, basically. There, controlled lightning bolt. And so here's a little video on a homemade cathode ray tube. Watch this.
This video will be split into 2 parts. The second part will go over the more technical aspects of the cathode ray tube and why it does certain things. The vacuum pump I'm using here is made out of an old refrigerator compressor. The power supply is made using a variac and an oil burner ignition transformer. The variac, also known as an auto transformer, allows you to vary the voltage coming from a wall outlet without altering the waveform. The output of the variac goes directly into the oil burner ignition transformer. Normally, an oil burner ignition transformer takes in 120 volts AC and steps it up to about 10,000 volts AC at 23 milliamps. But when I vary the voltage coming into it, I can either lower or raise the voltage coming out. The actual cathode ray tube was built using a wine bottle and some stainless steel wire. I drilled a hole into the side of the glass bottle carefully using a glass drill bit and inserted a wire bent in a half-circle shape. Then I secured it with hot glue to make sure it was vacuum-proof. As you can see, I made 2 of them, and they each have the wire at different lengths down the tube. To create a vacuum inside of the wine bottle, I just attached a hose bar into the vacuum hose and slipped a rubber O-ring over it. When the vacuum is pulled, the rubber O-ring sucks down onto the bottle, and it just seals itself. This way there is no epoxy or glues needed. Now it's time to power up the cathode ray tube. To do this, we need to attach some electrodes to the terminals of the oil burner ignition transformer. Next, we simply attach one of the other ends to an exposed piece of the hose bar and the other to that wire we added into the wine bottle. Now I turn on the variac and slowly and carefully turn up the voltage. As you can see, a beam of electrons, also known as a cathode ray, appears. It glows a bright purple color in my case due to small amounts of nitrogen and oxygen that are still left in the tube. Now, that time I was just running the tube on an AC current, so this time I'm going to add in a high voltage diode to make it a half-wave rectified current and see the difference in the beam. Now that we have that diode, let's power it up. As you can see, part of the beam that is glowing is only on one side of the tube. Last time it was on both sides, and there was a dark space in the middle. Now I'm going to demonstrate the magnetic deflection property of a cathode ray tube. Since it is a beam of electrons, it can be influenced by a magnet since electrons have a negative charge. Here I have a few magnets, and one side is marked with tape. When I put one side of the magnet that is marked up to the beam, it bends around it to the right. When I put the unmarked side to it, it bends around it to the left. Now I'm going to switch around the electrodes so that the electricity is flowing the opposite way. Now this time the dark space is on the other side. And when I hold up the marked side, now it bends around it to the left, and the unmarked side bends around it to the right. So depending on which way the electrons are flowing, they take a certain path around the magnet. Now I took out the diode and I'll show you the deflection of the beam when it's running on an AC current. As you can see, the beam appears to split around the magnet. Now, I told you earlier in the video that this is going to be split into two parts. The second part is going to go over the more technical aspects, describing why the beam splits and why it switches directions, if you're interested in that. I'll be using slow motion to analyze the cathode.
Okay, that was the end of video part 1.
When I hold up.
So this gives a very controlled way of studying electrons. This beam consists of a beam of electrons here. And they can tell that the electrons are charged because of the interaction with the magnet. If these were neutral, then the magnet would have no effect and the beam would just travel in a straight line. But since they're negatively charged, if these were positively charged, they would be deflected in the opposite direction. So they can tell that these particles are negatively charged. The next thing they can tell is that these particles are very light. And not only are they very light, they can actually determine how much they weigh. And so do you think you could take a single electron, you know, this tiny bit of an atom, and weigh it on the balance? No, you can't even weigh a single atom on a balance. And so how the heck are you going to weigh an electron? The way you weigh an electron is through physics and deflection in a magnetic field of these charged particles. And so based on the angle of deflection, you can figure out the mass. And we know the charge. And so heavy objects aren't deflected much. Lighter objects are heavily deflected. So you can just see based on that. And so they got the charge of the particle, they get the mass of the particle, and then they got to figure out, do these particles, are these particles found in all atoms? How can they figure out if these particles are found in all atoms or just the atoms in stainless steel? They're using stainless steel to generate the electrons here. Well, they can figure it out by this. Instead of using stainless steel, you use brass, you use aluminum, you use iron, you use copper. And it turns out no matter what metal they use for this, they got the same cathode rays, the same mass, the same charge. And so based on that, they concluded that electrons are found in all atoms. But did they test all atoms? No, they didn't. They just made an inference. So basically, if it worked for all these, then most likely it works for all. They can't use all atoms anyway because not all atoms conduct electricity. So that's a cathode ray tube. That's how the electrons were discovered. Let me jump ahead. We have two more subatomic particles. We we have the proton and the neutron. All right, the electron was discovered using the cathode ray tube with the CRT. How was the proton discovered? Well, the proton was discovered in a similar type apparatus, but you don't have to worry about how the proton was discovered. The proton was discovered by Rutherford. Thomson discovered the electron, but you don't need to know this. Rutherford is better known for something else, which we'll talk about. But the protons have a +1 charge, so we have unit positive charge, +1, which is not shown here. And the symbol that we use for the protons, P or P+. Okay, the protons weigh a lot more. The protons weigh about 1 U. Did they weigh those on a balance? No. They got the mass indirectly through physics. The neutrons are electrically neutral. They don't have any charge. And their mass is about the same. Not exactly, but about the same as a proton. So both a proton and a neutron weigh about 1 U. The neutron was discovered by Chadwick. It was given the symbol N or N0. And so for the proton and the neutron, we don't necessarily have to know how they were discovered. And we don't have to know who discovered them. We just have to know that they weigh about 1 U. One's positive, the other's neutral. And these are parts of the atom. Okay, then we're going to go back and talk about how those particles arrange. How those particles arrange is the structure of the atom. And there are two competing models for the structure, the plum pudding model and the nuclear atom model. The nuclear atom model won out, but let's briefly talk about the plum pudding model after our break. So let's take a break for about 10 minutes and then we'll start up again.